Hello, everyone. My name is Ljiljana Spasojević, and I will be your host for today's webinar. So welcome and join the webinar entitled From Equations to Impact, Translate Math Research into Real-World Solutions. So please note that this webinar is being recorded and that the recording will be available as soon as possible. I will briefly introduce MDPI, then our journal, and then I will introduce the chair. Okay, so MDPI was founded in 1996 in Basel, Switzerland. It has the mission to foster open scientific exchange in all forms across all disciplines. We have more than 400 diverse and open access journals, from which 9 are conference journals. And our journals are supported by more than 295,000 academic experts who share our mission, values, and commitment to providing high-quality service for our authors. AppliedMath is an international peer-reviewed open access journal on applied mathematics published quarterly online by MDPI. If during the webinar you have any questions, please feel free to post them in the Q&A box at the bottom of the screen. Please remember to mention the name of the speaker to whom you're addressing the question, as they will respond later. This is the program for today's webinar. Firstly, the chair will introduce our speakers, and then there will be a Q&A part. At the end, the chair will close the webinar. I will now give a brief introduction about our chair. So Professor Takayuki Hibi graduated from PhD from the School of Science at Nagoya University in 1987. He then visited the Massachusetts Institute of Technology from August 1988 to July 1989. He worked at the School of Science of Hokkaido University from September 19 to March 1995, and visited the University of Sydney from July 93 to November that year. In April 1995, he became a full professor at Osaka University and has remained there ever since. His research started with the study of algebraic combinatorics on convex polytopes, and then turned to Grobner bases, algebraic statistics, and computational commutative algebra. He organized the Japan Science and Technology Agency research project entitled Harmony of Grobner Bases and the Modern Industry Society from October 2008 to March 2014. He has published more than 200 peer-reviewed original articles and jointly wrote the textbook Monomial Ideas. So I would like to thank the chair for chairing this webinar and both speakers. And now, without further ado, I give the floor to the chair. Thank you.
Okay, thank you very much. My name is Takayuki Hibi, from Osaka University in Japan, and I am editor-in-chief of Applied Math. First of all, I want to introduce our Applied Math. As you might know, Applied Math is an international open access journal that aims to promote the integration of pure mathematics and applied area of sciences. It is devoted exclusively to the publication of high-quality reviews, regular research papers, and short communications that apply mathematical concepts, theories, and methods to other subjects such as physics, engineering, medicine, chemistry, biology, information science, energy, environmental science, finance, business, computer science, industry, and social sciences. On the other hand, ambitious papers on applied mathematics that will create new trends in pure mathematics are especially welcome. The aim of applied math is to encourage scientists to publish their experimental and theoretical results in as much detail as possible. There is no restriction on the maximal length of the papers. The full account of the research must be provided so that results can be reproduced. Electronic files or software that provide the full details of the calculation, proofs, and experimental procedure can be deposited as supplementary material if unable to be published in a normal way. Today's webinar, we invite two specialists on applied mathematics, Dr. Thomas Woolley from Cardiff University in UK, and Dr. Artur Chervinsky from Nicholas Copernicus University in Poland. And Dr. Woolley will give a talk on mathematical methods and their extensions to online tools. And Dr. Chervinsky give a talk on common mistakes in applied quantum theory to physical systems. And I very much hope that everyone in the audience will enjoy their presentations and the Q&A session that follows their presentations. I also hope that today's webinar will be a useful experience for you in your future works. Okay. Now we start the presentation. The first speaker is Dr. Thomas Woolley from Cardiff University in UK. I want to introduce Dr. Woolley shortly. Dr. Thomas Woolley studies mathematics at the University of Oxford from 2004 to 2017 and is now a leader in applied mathematics at Cardiff University. He specializes in translating complex biological and ecological systems into mathematical models. His research spanned diverse topics from understanding fish spots and zebra sprite to optimizing ecological resources and analyzing bat migration patterns. Recently, his work on COVID-19 modeling for the Welsh government informed critical public health policies, and he was awarded the Operational Research Society's Griffiths Medal for his contribution to health systems modeling. The title of Dr. Thomas Woolley is Mathematical Methods and their extension to online tools. Okay, Dr. Woolley, please.
So yes, no, thank you so much for inviting me to give this talk. I'm, as you heard, I'm a mathematical biologist. I'm purely a mathematician first and foremost. I did mathematics undergraduate, graduate, doctorate, postdoctorate. But I got a little bit bored initially, just by solving equations or proving things. I didn't know what they were for, didn't know what they were doing. So eventually, in my third year, there was a course on mathematical biology, and it changed my life, changed the course of my whole career trajectory, because it was the first time where the mathematics we used was really for something. We could predict population growth. We could say how diseases spread. We could track cancer growth. All these incredible, amazing things that would be useful to doctors, policymakers, engineers. So before I get on, this is just a variety of the problems I've been looking at recently and currently am. I've worked on bats. I'll be talking about that in a second. I've worked on understanding shell markings, sepsis, fingerprints, and more recently than the COVID-19 work. And what I've done is I've highlighted all the people there who aren't mathematicians, all the collaborators I've worked with, and all the people highlighted not mathematicians. And that's sort of my first piece of information, first suggestion, piece of advice, that if you want to get into applied mathematics and you want your maths to mean something, you've really got to go find people outside of mathematics that have problems that will interest you and interest others. So the first piece of maths I'm going to talk to you about is my work in BAT movement. And the thing I would again also say is if you are collaborating and working with people outside of mathematics, is that it's not a quick process. This work has been going on since 2017, and it's only just started to be published. So it really takes a while for you and your collaborators to gain a common language. So it can take years to really understand what is your problem, what techniques do I have, how can I help you. Let's carry on. So the problem we're looking at is that it's an ecological problem. Bats are small, they're fast, and they fly at night. They're also protected in the UK and many other countries. And trying to find a bat is a very labour-intensive process. So, for example, this is a map of the local Cardiff area. I work here at the Cardiff University School of Maths. I live pretty much on the outer edge of this ring, which is 3 kilometres away. So if I see a bat in my garden, I don't know if that bat is one of my colleagues in the School of Maths, or it could be learning French just to the north there. They fly a long way, and they're very hard to find. So what can we do as mathematicians? That's the first thing. What data do we have? If we're going to help, we need to know what data we have. And the data we looked at initially was trajectory data. The ecologists, they trap the bat humanely. They then attach a little tracker to its back and then release it. Now, this tracker could easily fall off. The glue they use is very light because they don't want to hurt the bat. So many trackers fall off. Tracking the bat even when you have got it attached is very difficult. And also the battery life of these things is very short because they have to be so small and light. So just working with this data, very, very difficult. But what does it look like? This is the kind of data we have. These are, each point you see there is a place where the bat was seen at a specific time over certain days. And then the diamonds that you see there are the roosts. So we know it came from one of those. We know where it was during the night, and it looks like a mess. It's very hard to see the signal amongst the noise. So we don't actually generally work with pure trajectory data. It's very difficult to understand. What we do instead is we use the mean squared displacement. What that means is we know where they start, that's their roost, and then throughout the night we say how far they are from their roost, that's their displacement. We square it, and then we average it over all the bats locations that we know. And that's what we track throughout the night, the mean squared displacement over time from sunset. And hopefully you can see from the data, it's much clearer now. We have clear signals. We have, for about an hour and a half, the bats spreading out. This is their dispersion phase. They're looking for food, insects to eat. And then from then on, the bats tend to head back to the roost. So I'm going to treat it as 2 phases. Firstly, their expansion phase, where they're moving out, and then their contraction phase, where the population comes back to the roost. Lots of work has been done on the expansion phase. Bats, anything, bats, wolves, deer, particles, spreading out is very easy to understand, particularly when you get a straight line for your mean squared displacement. We love a straight line because that is an indicator that it's pure diffusion. That your particle doesn't really know where it's going or care where it's going. It's just spreading out into the space to search that space. And that's very much what the bats are doing. They're just looking for insects to eat. But this second part of the motion, this coming back to the roost, very little work has been done on that. Hardly any I could find in the ecological literature. So we're really having to produce new maths. And that, again, that's another thing that I like to do when working with biologists, ecologists. The best collaborations is not just when you're applying your knowledge as a gun for hire to help the collaborator. It's when the collaboration really sparks some new experiments and new mathematics at the same time. So the model we used was a model first off of diffusion. The bats are spreading out. That's what you're seeing here. Each one of those little particles that are moving is a bat spreading out. And then over time, we have the particles being drawn back into the roost. Now, there's two ways we could do that. Either the roost acts like an attractant, or we could have the outside pushing the bats back in. So either the roost pulls them in, or the bats on the outside push them in. Both those techniques fit. You can happily fit both of models to the data. They both fit very well. However, the roost being an attractant, pulling the bats in, doesn't fit with the ecological understanding. The bats want to stay out from the roost as long as they can, because that's their foraging, that's their feeding period. So if the roost acts like an attractant, then the bats nearest would head back first, and they would stay in the roost for a long time. They would miss most of the night. Whereas this idea of the bats on the periphery, they're the ones most at risk. They're the ones that are perhaps the oldest in the group, whereas the youngest ones tend to stay near the roost. So as the night draws on and the sun begins to rise, those bats know they're in danger. They're most at risk. So they start to move back to the roost. As they move back, then we generated this idea of the leapfrogging. As they move back, then the bats that are now furthest out, they don't want to be furthest out. So you get this continuous motion of the bats leapfrogging back to the roost. And then, as you can see, you produce a mean squared displacement trajectory that looks a lot like what was seen in the data. Okay, so that was a piece of mathematics. That's nice. It tells us something about how bats move. That's useful for the ecologist, but not really very useful. But we can use it. So the second piece of data we used was static microphones. What you're seeing here is in each of these X's, these locations, there's a microphone. The ecologist goes out, they put their microphone down, and then they leave it for a week or so, come back, and hopefully, if it's not been stolen or trampled on by a cow or its battery's not run out, what you'll then have is a trace of when bats flew over. So these microphones pick up the bat calls and they record what they heard. So you're able to know when and where a bat was throughout the night. Okay, that's useful. We know where it was, when it was there, and we know how they move. So we can use those two pieces of information to track back where the bat hopefully came from and give an estimate for where the roost is. Now, to explain the data you're seeing a little bit better, we have the X's being the locations of the microphones. The circles around those X's are then proportions of how many calls were detected at those roosts, at those microphones. And then finally, in the center, we have a colored circle. That was the known roost. So in this data set that we have, we believe we knew where the roost was. We didn't use that as mathematicians to help understand the model that we made, but we used it at the end to compare our data with the actual solution. So how do we do that? Well, we know how the bats move. So what we do is we pick a point in our space and we say we think our roost is there. We then send out bats, simulated bats from that roost. Hundreds and thousands of bats. And some of those bats, as you see here, this is what's happening. So I believe that square, that black square there, is a roost. I send my bat out and they all travel in different directions. Some of them will cross the X's, the microphones, and then they will get recorded in terms of our simulation. Sometimes they don't hit the microphone, and that's fine. But what we're able to do is generate a simulated data set of calls and microphones. And then what we can then do is compare our microphone setup, simulated data, with a real data set. And we can say, okay, how close is our real data set to our simulated data set? And what we can do is produce a map of locations that are closer to the data and those that are further away. So in terms of the data that you're seeing here, the circle is the known roost, and the diamond is our best suggestion. It's where the error between our simulated data and the real data was smallest. Okay, that's a fine point, but any point estimate is probably wrong. I prefer these maps as the entirety of the data because they give you a nice, this is something you could give to the ecologist and say, okay, if you're going to be looking for bat roosts, look in this region here. This is probably the best point, but whether the roost is near there or not, we don't know. In this case, we do because we know where the roost was. But if I was to say to an ecologist, look in this roost region, look into this region for a roost, then you would be sure to pick up the roost if you didn't know where it was. Now, the two data sets you're seeing here were data taken from the same location, Buckfast Lee in the UK, but at two different time points. One was done on the 26th of June in 2019, and the second one was done on the 5th of September 2019. And you can see they give very different solutions to where they think the roost is. The first one in the 26th of June, we do really well. Our best guess is pretty close to that roost. But by the 5th of September, our estimate, our guess is not so good. Well, I mean, we do pretty well. You know, we're still closer than not knowing anything. But the region we would suggest that you search doesn't contain the roost. So we're actually saying you'd probably be moving further away from the roost. Or are we? So the circle in the center, that's where the known roost was. A few years later, they went back and did another survey, and they found this black square. This was a winter roost. So bats use different roost throughout the year. The circle was their summer roost. That was known. Later on in the year, they begin to use this black square, which is their winter roost. So what we can say is probably by the 5th of September, the bats have started to move away from their summer roost and are actually moving to their winter roost. That's the roost you would have found using our technique. So even when you're not finding the one that we know about, you can still find roosts that you don't know about. So yeah, this work is still carrying on. We're doing more useful things. We're now talking with the ecologists about how best to use the microphones. Where should you put your microphones? Because you don't want to put them all in one location. You wouldn't get much information. But also you don't want them too far spread out because you wouldn't get much information about where the bats are moving between them. So again, how is mathematics helping with understanding the problem? But one thing I should mention is all of this work so far hasn't used any landscape information, and that's probably wrong. The landscape definitely influences how bats fly, but the data we have is from very urban environments. So there's not many houses, there's not many roads, there's not much light pollution, which we do know affects bats, but the data we have, we don't need to understand it that well. So okay, that's the piece of mathematics that we do. Where does it then come into understanding, applying this and putting it online? Well, we were able to win funds from the government to actually hire a software engineer to put this online. So if you go to this link here, you'll get our app, and what the app does is it takes our mathematics and applies it. So you pick a point that you think is the roost, and it spreads out from there where the bats will fly. And this does take in the environment about what light is there, what buildings are there, what wooded areas, what water areas. And then when you understand that, as a developer, as a construction company, I can go in and say, well, actually, I want to change this. I want to put in a new road. And what that new road will do is add new lights. So that's what I'm doing in the second picture. That will then change how the bats fly, where they want to be. And you can see there's more of a bias to the right-hand side because the bats want to fly away from the light. So as a construction company, if I really wanted to build this road, then what I could do is then put mitigation factors in on the south and the east of the location that will help the bats thrive. Because if I'm cutting off some of their foraging territory to the northwest, I'd be better putting in mitigation factors into the southeast to ensure that my building construction is then given permission. The second problem that we looked at, or perhaps I've looked at many as I showed, but the second problem that we put online calculators for was COVID-19. Now, I tried to stay out of the modelling of COVID-19. I can do disease modelling, but everyone can do disease modelling. Disease modelling is for a mathematician isn't very difficult. I teach it to my 4th years. And everyone jumped on this bandwagon. There was lots of money and everyone was publishing about disease. So I tried to stay out of it. There's enough noise to signal ratio there. You don't need another person. But the Welsh government then contacted me and said, well, actually, we do have some questions for you. Being a mathematical biologist, can you help us? And so I have to help. But the question is, was any more resources given to us? No. So this was all very much done on a shoestring budget. The first piece of work that was done was by my students, and I was the mentor of the group. They did some really beautiful work. Lucy Henley, Josh Moore, and Tim Osler. They've all gone on to different careers now, but they did some really beautiful work during their doctorate. And it was all to do with this hackathon that the NERC, the Natural Environment Research Council, produced. What they said is, we have all this environmental data. Can you tell us how COVID is influencing and affecting the natural environment? We don't know what to do with it. Can you help us? So what they did is they went away and they thought about, well, okay, what can we do with this data? And what they had was CO2 data produced by public transport. Public transport, obviously very good because it's very efficient. It transports lots of people using the same amount of carbon as 3 people as 30 people. So if you can fill your buses and fill your trains, you're going to affect the environment less than if you've got 30 cars on the road. So wonderful to have good public transport. But at the time, we had the reason why they looked at trains was the local area of Cardiff uses a train network, and they were using diesel trains. And during COVID, you couldn't fill them because of social distancing. So how is social distancing impacting the number of passenger numbers, and how is that impacting how efficient trains can be? So what they did was they looked at how many people could you pack onto a train whilst maintaining social distancing. The problem with that is getting an optimal packing solution is very difficult. Now, if I were to ask you, how do you pack circles together? Then if I gave you 1, 2, or 3 circles, they're not too difficult, fairly trivial solutions there. You can't do better than just 1 circle. It's 1 circle. And 2, you have to put them together. Any further apart, you're wasting area. 3, what better? You could put them in a line, but that's obviously worse than putting them in a triangle formation. But what about 4? Well, there's perhaps 2 obvious ways of packing 4 circles. You can either use a rhombic structure or you could use a square structure. And it turns out, I mean, have a guess. I won't come back to the audience, but before I tell you, have a guess. Which of those 2 structures actually is the better, contains the least area, I should say, if I were to put a box around them as my train carriage? Is it the square or the rhombus? Well, it turns out the square packing is actually better. If I were to put a square around that, you waste less area than if I were to put a rectangle around my rhombic structure. There's more area wasted in here and here than there is in these little pieces around the circles. Is that obvious? Absolutely not. If that's not obvious, what happens then when I ask you to pack 11 circles? What's the best way to pack 11 circles? Turns out this is the best. Well, I don't know if this is optimal. I just know this is the current optimum that we found. Certainly not intuitive. Certainly not a shape I would think to produce. So this gives you an idea of how hard packing is. You need huge computational power at the moment, and to really try all different combinations. So what the students did was not to try and find an optimal solution. They just tried to find a good solution. So the first thing we do is bound. What possible solutions could we get? Well, if we put a person in the corner and they have a 2-meter radius social distancing bubble, then we can't put anyone in this region here. Okay? Then the next person we can use is there. Okay? That blocks out 6 seats. So we keep putting those people along. What's the maximum number of people we could do? Well, there's 96 possible seats they could have. 96 divided by 6 of seats we can't use, that gives 16. So we should be able to put 16 people in this carriage as sort of the most packed version. Now, if we weren't so worried about packing and we were a bit more relaxed, then we could put our people in the middle. Very bad packing. For each person then, we knock out 12 seats. 96 divided by 12 gives you 8. So somewhere between, we can fit 8 to 16 people in this carriage. And the closer we get to 16, the more optimal we are. So what did they do? They used a greedy algorithm. Okay? They didn't try to get optimal. They just said, pick a seat at random and place the next person outside a 2-meter bubble and keep going until you can't fit any more. How many people can you produce? Do that 1,000 times, using different random initial seats. See what's the best you can get. They also then put shielding in. So it wasn't just a case of free space. You could then say the shields blocked airflow. And this is what they did. They produced this wonderful GUI. Again, you can follow the links, find the GUI online, play around with it. Absolutely fantastic piece of work. And they won the NERC hackathon with this. Because, you can literally put in what's the social distancing, how many shields are there, where are the shields, and the length, all these wonderful things, and you get an immediate answer. And this was then written up and used as evidence in the UK Parliament for understanding firstly, how was COVID managed on public transport, and what was that effect. There also came out a nice little result. So at the time, the maximum number of people we could get onto the trains was around 14 in terms of the actual packing we could do. But the black line that you're seeing here, this black line, is the train. As you put more people on the train, the amount of carbon per person that a train outputs drops because it's per person. Fantastic. But we couldn't put that many people on the train. So in terms of how much carbon we produced, that comes to here. This is the level of carbon that a fully packed, socially distanced train would produce. Let me clear. There we go. But the amount of carbon that a small family car would produce is then there. It's slightly better. So at the height of COVID, it was actually slightly better to simply drive your small family car to work, and it probably even better for your health, because then you weren't even in a train where the airflow wouldn't be great. Wonderful little result that perhaps not the best result. We don't want the cars to be the best efficient use, but at the time, because we were using diesel trains and because we were socially distancing, we couldn't pack the trains as much as we would have liked. This then on to another piece of work asked by the government, which was, this was coming to Christmas, and we were then going to release a load of students from the university back to their families. Christmas, of course, a time when lots of families get together, older families, younger families, all getting together. So a critical time for not spreading COVID. COVID ran rampant through the universities because quite a lot of the time the students live very close together. So you only need one person to bring it to immediately pretty much infect the whole university. So we were asked, based on how many students we were sending home, how many secondary infections would we expect? The mathematics here is very simple. Number of students times prevalence, how many students will be infected, times the secondary attack rate of the disease, we got that from data, times the number of people in the family. And we varied that from 2 to 6 based on the Welsh census data. Very simple formula. But the problem was the data kept changing because Welsh government would, what about this? What about this? What about this? And what we saw, we were lagging in this loop. We could do the maths very, very easily, but the time it took for them to email us, for them to put us in the formula, to then get to them to give them a result and then get back to them, very, very slow process. So what we did is we created this online calculator where the person could put in whatever numbers they liked and get an immediate solution. And they loved it. It was very quick, very fast, helped them produce their policies a lot faster. And from this, it was then decided what policies were put in place. And so what we had was tests to go home before we let the students home. We would test them. We also had staggered leaving dates. We didn't just release everyone at once. We let certain groups go home at certain times. This led into creating the intervention simulator. We were asked to look at small educational environments. We're not looking at population, the population of Wales. We're looking at what happens in a classroom. We got some money from Just One Giant Lab. We got I think it was like a 3,000 euro, 4,000 euros, something like that. And we were able to pay one of the doctoral students to produce this. So hopefully if I can, again, hopefully you're seeing my web browser now rather than my presentation. This is what, as you can see, was done by Josh Moore. And what we have here is, firstly, you can unwrap the information, tells you how to use it, what it's all about, some nice videos on how to use it. Put in all the infection parameters you want, how many agents, how infected they are, their social group size, interventions. When do you do your testing? How do you do your testing? What's their false negative rate? Very important. And then when do they get together? When do they test? You can vary all of this. And then on top of that, you can send all of this to the server. It runs the simulation very quick, very nice, and very quickly gives you results. Again, the maths is easy, but we need to put that power of the maths into the hands of the people that make the policy. This has then led into working with architects, in fact, and creating another online simulator where we now include the building geometry. So let me go back to my presentation now. Again, you can go to this virus.app and you should be able to. So this is the online simulator. And what it allows you to do is put in geometry of a real building. This is a care home that we were asked to look at. And for the architects, their software produces really lovely buildings very quickly, very easily. For mathematicians, disease simulation is very easy. Putting them together wasn't trivial. That was probably certainly the hard part, getting everything to talk to each other in terms of geometry, location. And also all of these people, you can give them agendas. Where are they? When are they? What are they doing? Are they running? Are they singing? Are they speaking? But putting all of this together, then you can use the virus.app. And we're hoping to get some more money to then keep developing this. Because again, none of this is difficult. It's just getting it into the hands of the right people. And so that brings me to the end. So there's just some final words I'd like to say about working with collaborators and government and all these different things, is that mathematicians have huge amounts of techniques that can help outside of our discipline. You know, we work with data, we work with models, we can test hypotheses. Critically, the best collaborations aren't just about statistics. That's what I found. I can do statistics. I'm not a big statistics fan. If I'm just saying, what does my data say? I'm not interested really, because what I want to know is beyond just correlation. You know, you see this quite a lot. You know, people have a big data set and they throw AI at it and do some machine learning, and that's fine. You get correlation. But what's driving that correlation? That's what I want to know. What's the model behind it? That's where I come in. That's the mathematics that I enjoy doing. But how we've been able to not just do the maths, but put the maths online, put these calculators in places that people can use them. Well, first off, if you can get money, that's always the best option, because then you can hire people who can do the software better than you can. But if you can't, then R is a good place to start. If you can code in R, then you can get a software package called Shiny Apps, which you can use your maths as the background, the motor, and you can build graphs and switches and buttons on top to make a nice GUI. And it's all fairly simple. But the final point there is you have to be interested in the problem. It can't be just a case that you're a gun for hire. If you don't care, it won't lead to a good collaboration. If you are learning something, if you're finding new maths in the biological application, the physical, the chemical application, whatever it is, you'll produce some good maths, you'll produce some good applications, and hopefully then you can then drive that passion into producing online calculators. And so with that, thank you very much for listening. Any questions?
Okay, Thomas, thank you very much, for your very elegant talks. Is there later we will organize a Q&A sessions, but now is there some questions from the audience? I want to just ask to Thomas. So in the beginning of your talk, you said you first studied pure mathematics. You said, yeah.
I studied a variety of pure and applied, but during my degree at Oxford gave a very pure, even the applied side was very pure. So like I say, there was this course in mathematical biology which really changed what I saw mathematics could do.
I see. Yeah. Okay. Okay. Maybe later we can also discuss. In the Q&A sessions. Okay. In any case, thank you very much, Thomas. For your very elegant talks. Yeah, I very much enjoyed your talks. Thank you very much. Okay. Now, I want to introduce the second speaker. Second speaker is Dr. Artur Czerwiński from Nicholas Copernicus University in Poland. Okay. I want to introduce Dr. Czerwiński briefly. Dr. Cherminsky received his PhD in physics in 2018 from Nicholas Copernicus University in Poland, with a focus on mathematical and quantum physics. He has conducted research at multiple institutions, including the Institute for Quantum Computing, the Center for Theoretical Physics of the Polish Academy of Science, and held a postdoctoral position at the Center of New Technologies, University of Warsaw. And Dr. Cherminsky is currently assistant professor at Nicholas Copernicus University and lead researchers at Startup PL, where he is involved in ESA-funded project of quantum technologies, including space-based link for the quantum internet. Okay, now the title of Dr. Chervinsky's Common Mistakes in Applying Quantum Theory to Physical Systems, a case study. Okay, Dr. Chervinsky, please.
Yeah, hello everyone. I thank Professor Takayuki for this very kind introduction. I'm also thankful to the organizers for inviting me to this webinar. It's an honor for me to give a talk at this event. I'm an editorial board member of AppliedMath since 2022, so it's been 3 years. And as Professor Takayuki said, I specialize mainly in quantum physics, quantum technologies. So my contribution to the AppliedMath journal relates mainly to making editorial decisions on manuscripts that relate to physics, to applications of mathematics in physics. Well, yes, first I want to tell you a few words about my group. My group is called Single Photon Applications Laboratory. The leader of this group is Piotr Kolenderski, who is my supervisor at the moment. And our group specializes mainly in two kinds of topics. So we can talk about quantum communications. So this is applied topic connected with quantum technologies. And we talk about more fundamental research topic that is connected to photon-atom interactions. As for quantum communications, we have like two different lines of research. So we talk either about fiber links or satellite links. So these two environments are completely different for quantum communications, so they require different, also different methods and different phenomena have to be taken into account if we talk about these two situations. And I want to give you some idea about what we are currently working on. And then I will move on to the main topic of this talk, that is a case study about mistakes in applying theory to specific physical examples. So let me talk briefly about some examples of research that we've been doing about fiber-based quantum communications. So here, for example, of course, we have to talk about single photons and the properties of single photons. So this is the main distinction between classical optics, where you can look at the power of your light beam, and talk about properties of a light beam that consists of many photons, and then this microscopic this object behaves differently than single photons, where you have to look very carefully in this micro scale to talk about properties of single photons. And for example, we want to describe temporal properties of single photons. So when you want to describe the position of your single photon in the time domain, in the quantum world, you are never sure where your object is, but you may have only a specific distribution that can give you a quantum wave function. So, for example, we use Gaussian-like wave functions, like you can see here in the middle, and from this Gaussian wave function, according to the rules of quantum mechanics, you can compute a probability distribution. So this temporal wave function of a single photon in general may have like two parameters, one sigma, which is connected with the width of this wave function, and the other, this capital C, which is like a complex phase, which can be controlled. It can be introduced experimentally. And in one research, we were interested whether this particular parameter has some significance in quantum communications. Of course, if we want to model quantum communications, we have to take into account different events, different phenomena that affect our single photons. And in case of fiber-based quantum communications, two critical situations, two critical problems that we absolutely have to take into account. I described here at the bottom of the slide. So it's chromatic dispersion, because it affects the temporal shape of the photon. So we know a specific operator that has to be introduced. It acts on the wave function, temporal wave function, and we can compute the result after propagation for a fiber along the fiber with length described by capital L. On the other hand, we have detector uncertainty, which is connected to the measurement of the arrival time of single photon. So every detector has certain profile that can be modeled with the Gaussian distribution. So we have also this effect that has to be taken into account, that detector introduces like an additional sort of noise to your measurement results, that they are affected by detector's uncertainty. And as I said, we were interested in this particular parameter, capital C here. It is called the chirp parameter. We were interested whether this value can affect quantum communications. And if you model the performance of a specific quantum key distribution protocol, you usually get results that look like the plots that we have on the right-hand side. This is the plot denoted by B. So we usually model it in the domain of the fiber length. So we see how the amount of key changes as we increase the propagation distance. The amount of key is here modeled in a probabilistic manner. So as I said, we look at single photons, and then all the computations are made in a probabilistic manner, because the amount of key that we can receive per photon is actually a probability that this particular photon will generate a meaningful signal for our QKD protocol. So it's a probability that from this photon we will get a meaningful bit of information for our secret key. So this is this capital K that we have on horizontal, vertical axis. And as we can see, yes, this quantity sort of declines as we increase the fiber length. And here we can compare the results for 3 different values of the detector's uncertainty. This is the so-called detector's jitter. It is either 4 picoseconds, 25 picoseconds, or 35 picoseconds. And we can see what was expected, anticipated, yes, that if we increase this jitter, so we increase the noise that is introduced by the detector, then the amount of key declines more rapidly, and also the distance for secure communication is shorter. But what is even more interesting, we were particularly interested in this capital C parameter. On the left-hand side, we plotted the maximum distance for secure quantum communication versus this capital C parameter. And what we found out was the fact that this plot has a clear maximum. So there is a specific value of C that maximizes the secret key, the distance for secret communication. And then we took this particular value, which as you can see is like slightly negative because this maximum is shifted a little bit to the left from 0. And we computed again for this particular optimal value, the secret key rate. And it's represented by this dashed line on the right-hand side picture, right-hand side figure. And we can clearly see improvement in quantum communications if we select this optimal value. Yes, as you can see, we have like pairs of plots, and we compare a plot which is given by a continuous line for C equals 0 with this optimal value that is slightly negative. It was in one case minus 0.2, in 2 cases it was minus 0.25, and we clearly can see improvement. And this particular research shows the importance of proper control of parameters, right? Because this small C parameter, which is like a complex phase, has some mathematical meaning, but we can see that it also has physical significance, yes? So it can lead to a visible improvement. So these were some examples of research on fiber-based quantum communications, where probability theory is very important. Now I want to talk a little bit about my research connected to space-based links. So we have a project from European Space Agency that is called Space-Based Links for the Quantum Internet. And in this project, we want to simulate the performance of a quantum network that will consist of a number of satellites that encircle the Earth. And from those satellites, we can distribute pairs of entangled photons to optical ground stations somewhere in Europe. And we can perform different use cases. So we can use those entangled photon pairs for different specific applications. Yes, and one of those applications is again QKD. So we can use entanglement to be able to generate secret keys and then exchange information between two parties located somewhere in Europe. And the other use case is connected with distributed quantum computing. So we all have heard about quantum computers, and we know that those machines are expected to increase computational power. But we can imagine, we can also think of creating even more powerful quantum computer if we just interconnect two quantum computers with entangled photons. So those two quantum computers, if they share entanglement, if they share multiple pairs of entangled photons, they can be interconnected and they can perform some algorithm even more efficiently because they will operate actually as a one quantum processor. So this is something that we are working on currently. And here I don't want to give you any formulas, but I just want to tell you about a particular problem, particular challenge, I would say, that we have and everyone has who is dealing with like free space or satellite-based transmission of optical signals. So we have to take into account different processes that occur in the atmosphere as we propagate our signal from a satellite to optical ground station. So here we have this. Here we have simulations. These are just examples of what is absolutely necessary. This is an absolutely necessary element of those simulations, that you have to know how much of the signal will be lost due to the transmission from a satellite to the optical ground station. Yes, and as a satellite passes above your head, then we have this angle that appears on the horizontal axis. So 0 corresponds to zenith. So it's a situation where you have a satellite exactly above your head, and then the larger this angle is, then it means that the satellite is closer to the horizon. And we can simulate losses for different telescope diameters, for different orbits. Here we have LEO orbit, so low Earth orbit, and medium Earth orbit. So we can compare different situations and consider trade-offs for that. Because obviously you see that here, if you have a satellite on LEO orbit, low orbit, then the losses are smaller. So you would think that, okay, it's more beneficial just to go for the LEO orbit, but not necessarily that must be true, because in MEO orbit you have larger losses, but the time for communication, so the visibility time of the satellite, will be longer. So then it may turn out that you might be able to exchange more information. So different advanced mathematical methods are applied to simulate stuff like that. Finally, we have a project about multidimensional free space quantum key distribution protocol. So it's a very advanced mathematics that has this goal to further advance quantum communications. Because usually when you talk about QKD, you mean a situation where you encode information in the polarization degree of freedom. So everyone has heard about polarization. We can distinguish different polarization states, and we can use them to encode 0 and 1, and then qubits, so different superpositions. But if you have a single photon or a pair of photons, you can actually talk about different properties of those objects that allow you to encode information. So we have polarization, we may have time, so we can use the arrival time to encode information. So depending on the arrival time, you will have different states. You can use frequency. And the hypothesis is that if you combine like several degrees of freedom to encode information, it can be even more efficient. So you can benefit from those, from the fact that you will apply different dimensions, different degrees of freedom. So this is just some idea of how advanced mathematics is applied in quantum technologies. Now I want to move on to the case study about some mistakes that you can encounter if you are looking at mathematics that is applied to specific problems. So as I said at the beginning, we are also interested in our team in photon matter interactions. This is fundamental research, but strictly connected to what we are doing in other projects, because it's about how photons, how we can first excite atoms, and then what kind of properties we can see if we measure the light that is emitted by our atoms. So we were interested in the problem of superradiance, and we have found a very nice publication from Nature Communications from 2017. And our idea was first to simply follow this publication and use the mathematical framework from this publication as a sort of background knowledge, as a sort of framework that we can further develop. But unfortunately, when we were reading this publication, we have found many inaccuracies and many physical problems. So instead of following this publication, we decided to write a comment about those inaccuracies. And you can see here the title of this comment, and it's a joint work with my PhD student Jakub Borkowski, and as I said, my supervisor Piotr Kolenderski, who is the leader of the entire group. And we posted this comment on arXiv. It has already gone through the peer review process, and soon it will be published in Nature Communications as a sort of comment that will accompany this original publication. And this example is a good case study, as I said, and I will explain why in a moment. So this article from Nature Communication is about superradiance, which is like a particular process, particular event in the problem of photon matter interactions, because it's a collective emission. So in this case, we have a group of atoms or quantum emitters that are excited and then emit light more intensively and more rapidly than in case of individual emission. So we want to study this process because it's a specific source of light with the very unique properties. So we want to study it with the potential of future applications. But let's talk first about why we were attracted by this paper. So here, as you can see, I just copied some graphs from this paper. Yes, the sources is provided. So at first, we thought that this paper is like a perfect contribution to physics. Because if we talk about physics as a discipline, we can describe physics in two ways. Yes, first, physics is of course experimental science. So if you want to talk about specific processes, specific phenomena, ultimately you would have to provide experimental proof that this event actually takes place, it happens. On the other hand, we know that physics is a precise science that requires advanced mathematical models that allow us to describe those processes and those events that we observe, yes? And if we look at the contribution, this particular contribution from Nature Communications, we can see that it was like a perfect combination of theory and experiment, because they showed some plots that were from experiment, and then they presented their model, theoretical model of superradiance, and in those plots they showed that these two things match, so they are more or less the same. So it's a perfect situation for a physicist. Yes, we have both theory and experimental validation of this theory. But when we took a closer look at those theoretical foundations of this model, we actually started to notice more and more mistakes, more and more problems. So first situation was that this paper was also posted on arXiv, and when we compared the master equations for our superradiance in those two sources, we saw some differences, yes. We decided to follow the published version because the version that is on arXiv, it's a preprint. It may still have some errors that were corrected later on. So we decided to follow the mathematical formalism as in the paper from Nature. So we took their exact equations and we tried to replicate the results. So it's a common approach, common situation, yes. Actually, any researcher should be open to this kind of situation. Yeah, if you publish some model, you should be ready that someone will take the model, will take your equations, will follow your way of thinking, and will try to replicate the results. So first, this model depends on the number of those emitters. Here, the NV centers are the emitters, and depending on the number of the emitters, we get different plots. So first, our PhD student simulated this process for 2 NV centers, and we already saw some disagreement. Yeah, here we have model A, model B. Model A is based on Nature Communications. Model B is the model after some improvements that we have done. So we already saw some differences, but the main problem was observed when we increased the time scale. So it's actually a very important conclusion and sort of advice, yes? If you model something in the earlier case, when the time scale was shorter, you were not able to observe all the properties and the behavior of this model. But if you increase the time scale, you see an obvious problem, yes? That we have different asymptotes for those model, and the model based on nature communication actually gives a positive asymptote. So it means that the normalized photon counts from emission actually they should go down to 0, and this is what we have in case of model B, but we don't see from model A. So actually this emission of photons still happens even when time goes to infinity, yeah? Which is obviously a physical problem because it does not agree with what we expected as physicists. Then we started to test different variations of this model. So we, for example, took 7 NV centers, 7 emitters, and then we compared again model A, model B. We saw even more problems in this case because we saw that the plot that we got from their model does not look absolutely like the plot they published in their paper. And the plot that we obtained has, yes, important problems because first we can see here that it has negative values, and with those vertical lines we mark the points where this plot goes to 0. So in between we have negative values. So this behavior does not reflect what we would expect. And again, if we just increase the time scale, we would notice that the asymptote is not 0 from model A. Then we had a very bizarre plot for 10 NV centers. So again, we can compare the result on the left-hand side, model A, that we obtained with the result on the right-hand side that they published in Nature Communications. So we can see that those plots are completely different. And then again, in case of the plot that we simulated with exactly the equations that they published in their paper, we see that this plot does not reflect the properties of photon emission, the properties of fluorescence, because here we can clearly see negative values and the fact that the asymptote is not 0. On the other hand, if we simulate the process with our equations, we can see that all those properties, all those conditions are ensured. So this plot for model B is strictly non-zero, and the asymptote is 0. So as you go with time to infinity, then the plot drops to 0. Yeah, here we have the asymptote computed for 10 NV centers. As we can see, it's very, very high. So again, we have this situation that the fluorescence still happens even if you go with time up to infinity. So by looking carefully at this model, we identified numerous problems, numerous mistakes in all the formulas that describe the dynamics of the emission. Well, I don't want to go into the details. If somebody is interested, particularly in this topic, you can check our paper. As I said, it will be soon published in Nature Communications. But yeah, the comparison of those two models allowed us to identify 9 critical mistakes, and the reasons for that mistakes was different. In some cases, it seemed like just a typo, so the sign was changed. In 3 cases, it was problem with probability with the proper interpretation of probabilities. So we know from quantum mechanics how we can compute probability amplitude of a certain quantum state, whether it will be transferred to another quantum state. So we use the scalar product. But in this case, they sort of used, instead of this probability, they used the probability of opposite event. So it's 1 minus the probability that comes from quantum mechanics. We also noticed some problems with proper notation, like in the second line of the dynamic model, we have this A factor that is 2j. So this factor was probably by mistake put in front of the bracket so that it multiplies 2 elements inside the bracket, but it should be actually put in the middle of the bracket so that it multiplies only the first element with capital P, J, M. So many errors, and in our comment we actually discussed in a very detailed manner the origins of those errors, and we demonstrated that our model is consistent with physical interpretations. So it's not only mathematically accurate, but all the results that we get from this model are physically appropriate, physically correct. And if we were to somehow summarize this case study and give some maybe general conclusions, yes. So if you want to model a dynamic process, so you have to use sophisticated mathematics, but you have to be very careful and just ensure that all the properties that specific operators, for example, in this Lindblad form, those specific properties are ensured. You have to pay attention to probability. As we know, quantum mechanics, it's all about probability theory. So you have to pay a lot of attention to probabilities and proper interpretations of probabilities. Then you have to, in general, yes, it's a very general advice just to verify how your model behaves in long time limits. So you always have to check the asymptote. Quite often when we compute some quantity in physics, it has to be non-negative. Yeah, many of the quantities in physics has to be non-negative. So it's important also to verify whether your model ensures those physical properties, yes. Yes, and a few more like practical advice to test some extreme cases, how your model behave if you substitute 0 for a specific parameter, if it's allowed, of course, just to test whether it's all logical and the interpretation is fine. Yes, and stuff like just to verify the model in the existing literature and publish the code for transparency. So as I said earlier, if you work in science, you should be open to kind of criticism, yes, and also to the fact that somebody may follow your methods. So if there are some problems with your model, sometime in the future, yes, it may happen that somebody will write about those issues. And just the last slide with the literature that I used. So our comment, yes, and different versions of the paper that we commented, and also the paper about QKD that I discussed at the beginning. If you are interested in those topics, you have also my email, so I am open to any collaboration or discussion. So that's it from me. Thank you very much for your attention, and let's start the discussion.
Okay, thank you very much, Dr. Chervinsky. And just a quick question. Your title is Common Mistakes in Applying Quantum Theory. So I want to ask you, what is the most important to avoid the mistakes? To avoid mistake, what is most important in general?
Yeah, in general, of course, it would be, first of all, good to have a solid mathematical foundation, yes?
Mathematical
So
foundation. Yes.
sometimes we also see papers where people who work purely in experimental physics try to use some formulas, yes, to describe their results. And in that cases, it might be actually very visible that they are not specialists in theory. So as I said in my presentation, like in physics, this dream is to combine theory and experiment. Yes, it's always like a perfect situation where when you have advanced theoretical model and you have experimental validation. Yeah. So if somebody works in experiment and they want to just create some framework to describe the results, so the most important thing would be to either learn about mathematical modeling from reliable sources, or just to collaborate with someone who is a specialist in this kind of field. Yes, so they can avoid mistakes. Yes. So this is one thing, like solid mathematical background. And the other thing, as I said in my presentation, yes, it would be always to remember what you want to model, yes, and what are the properties of this particular physical quantity, yeah? How it should behave. Because more or less in physics we have a lot of intuition, yeah. So it's not often that we are surprised with the results, yes. More or less we always know how something should behave, yes, and how it should react if you change this parameter on that parameter, whether it should increase or decrease. So it's always an opportunity to make tests, yes, and see how your model behaves, whether it reflects the expected properties. Yes, so this is what I would say.
Yeah. Okay, thank you. Oh, I want to ask also to Thomas the same question. What is most important to avoid the mistakes?
I fully agree with the answer there. The collaboration. Find the best
Collaboration.
people who collaboration. Yeah, find the best people who know what they're talking about. So, I work with biologists, and biologists know they're taught a bit of statistics, and because of that, that can lead to a lot of problems because they think they know what they're doing. And I don't want to speak bad about biologists because they know what they're doing in the lab. They know what they're doing with their cells. They know what they're doing with their proteins and peptides. I know none of that. So if I ever talk to you about what a cell can do, ignore me completely.
Yeah.
If I tell you about reaction diffusion equations, there I know what I'm doing. So it's all about trusting someone as much as they are the expert in that field.
I see. Okay, thank you very much. We have still 5 minutes. In the Q&A box, Q&A box, there are some questions. So in Q&A box, there are 6 questions. Yeah, some questions. Okay, some questions to Chervinsky, Doctor. Can you answer just the first question? You can see the Q&A.
Yeah, I see this question. Yeah, it's about PhD student, yeah, or a young
Yeah. Based
scientist.
on your work, how should a PhD student or a young scientist approach? This can you answer these questions?
Yes. Yeah, so it's a good question, yeah, because PhD students who actually start their career in science, yes, when they take a publication from a top journal, they might think that it must be 100% true and correct because it is published in Nature or because it is published in some other top journal. But actually, yeah, I would have to advise such students just to be careful and just to think about what they are reading. So especially when we are talking about theory, yes. So in this case, it might be easier to verify the formulas. Because we talk about mathematics, yes, it's a strict science based on logic. So although researchers, they often try to skip the computations that they think are not necessary. So they just say that if you perform some kind of operation or if you apply some operator, you get this result, and they don't show any computations just to, you know, make the paper shorter. So within the mathematical methods, you are still able to compute even by hand, yeah, step by step, how specific operators act on your quantum states or wave function or and so on. So this is like one method, yes. So you would have to just try to compute some rederive, yeah, some equations just by yourself. Yeah, again, compare with different sources, especially if you are talking about some classical models, well-known models. So in this case, you could just compare a few publications. Because if you take one publication, there might be even like a typo, yeah, because somebody just changed the sign by accident, yeah, it don't have to be on purpose. So if you compare in few sources, yes, then you will see whether it is correct or not. Yeah, so this is what I would say here.
Okay. Yeah. Okay. Thank you, Betch. Okay. Finally, I want to ask a question to Dr. Uri. Yeah. What is your further work? Your work in COVID-19 is quite interesting. Yeah. What is in your future work? What do you
Well,
mind?
the
The
future
next
work on the
project.
COVID-19 stuff
Yeah.
is to look more at realistic geometries. So I showed that right at the end there. So we're currently working on that. The geometry, the piece we've got from the architects, that can work in 3D. And as yet, according to the architects, no one's worked on three-dimensional structures of disease spread. Now, disease spread in 3D is no harder, theoretically, than disease spread in 2D or 1D, in fact. Computationally, huge amounts more difficult. You know, the curse of dimensionality, as it's called. So we're currently working on trying to, can we do three-dimensional reaction diffusion simulations in time that's usable for real life? You know, we can do it, certainly, but they can take overnight to run. So we're trying to use various techniques like hybrid methods, coarse grain simulation, things like this, to just make 3D simulations fast but also accurate. That's the key thing.
Okay. Okay, so now we must close this webinar. Okay, I want to thank you for both speakers, Dr. Chervinsky and Dr. Uri, and all participants. Yeah, thank you very much. Okay, so
Thank you.
is there some announcement from the host?
Okay,
Hmm.
thank you for everything. But we have some other questions here. Would you like to address them as well in the Q&A box?
Yeah.
So I see a question that is addressed to me. It's about probability. So I can answer this question because it's about my talk. So the question
Thank you.
is about one of the conclusions that I mentioned on my slide, that we should be able to distinguish different types of probabilities. So I actually meant that, for example, in QKD problems, yes, as I said, we work with single photons and it's all about probabilities, yes? So we have to compute the probability that this particular photon will generate a meaningful signal in our detection system. So it's about computing total probability of this event, that from source this photon will reach your detection system and make a meaningful signal. But on the way you have different events and different problems. So you compute total probability that has to take into account all those events. Yes. So my conclusion from that presentation was, in that case, general, that you should be able to distinguish different types of probability, whether you have sometimes conditional probability of observing photon under specific circumstances, or whether you have total probability, whether you have joint probability. So this is what I meant, yeah, that in general, if you want to work in quantum physics, you need to have a good understanding of probability theory just to be able to assign good probability measure to all those events, yes. And in case of the mistake from Nature Communication, yeah, as I said, those authors, they just confused the probability of the event. So it was like the squared modulus of scalar product. So they confused this detection, this transition probability with the probability for the opposing event. Yeah. So they, I don't know why, but they took 1 minus the result of quantum computation. Yeah. The probability from quantum mechanics. So this was my general advice, that good background on probability theory is necessary, in my opinion, if you want to work in quantum science. Yes. So it's a very general conclusion, but it's true.
Okay. All question. Is there some question to Dr. Uri?
So we also have question from Precious Amadi. I see that this question is also addressed to me because it's about publishing
Yeah.
the code. So Precious talks about GitHub, which is, I think, a good platform to publish such resources, because usually you can't put code as a kind of supplement to your paper. Usually, I haven't seen a situation where it could be a part of your publication. So you should just find some alternative platforms to publish your code. And yes, GitHub is a good platform. Yeah, a lot of users, so you can reach to the people who might be interested in this code. But also I could suggest ResearchGate, which is like a Facebook for scientists. And in ResearchGate, you can actually put any research on ResearchGate and make it available right away. Yes, so without any delay, you don't have to wait for the announcement like we have on Archive. So ResearchGate is a very I would say useful tool to support open science. So in this context, it is important. So you can put your preprint on ResearchGate, and then you can also add any resources that you want. Yes, so you can add them as the supplementary resources. So it can be your code, it can be Wolfram Mathematica files, because, for example, in my case, I use very often Wolfram Mathematica. So you can put this file, so it can be any file, yes? It can be just pure data, for example. You can also put it on ResearchGate and connect it with your paper, yes? Because it will be like a resource that accompanies your paper. So yeah, we have many platforms that we can use to support open science. So that would be my answer. Yes.
Okay, and another two questions. Question from Stepien. Two questions from Lucas Stepien. This is to whom? This is also quantum physics. This is also to Dr. Cherminsky. These questions. Lucas.
Yeah, I'm reading them right now. I see that we have even some references in those questions.
Yeah.
Well, I'm not be able to answer to those questions right now, because I
maybe
see
then,
that
yeah.
it's about some deeper understanding about logic and the relation between mathematical systems and physical systems. Well, I'm not sure, but yeah, I'm open to discussing it maybe later. So
Okay,
if
maybe
if this
yeah,
person
you
has
can
my
discuss
email,
later.
I can contact
Okay.
him.
Yeah, good.
I will also
Okay.
copy the reference, so I may get in touch with him just after the webinar, because it seems really relevant, but I'm not able to answer it, spontaneously right now.
Okay. Okay, then, thank you very much for all participants, and also thank you very much for the MDPI host. Yeah, thank you very much. Oh, I very much enjoyed. Yeah.
Yes, thank you very much.
Back to the host. Yeah. Okay.
Thank you very much. I also enjoyed it. I would
Mm.
like to thank you, the chair and the speakers, for your presentations. It was very, I think, interesting and very useful. And I hope it was like that for our attendees and that they enjoyed it and learned something new. So the recording will be available as soon as possible, as I mentioned. So we will let you know, and you can find it on our site forum. And that would be all. Thank you once again. It was a pleasure.
Thank you very much to organize this kind of very nice event. I very much enjoyed it. Okay, thank you very much.
Yeah, thank you very much.
Thank you.
Yeah, see you again.
Thanks.
Have a nice day, all of you. Bye.
Nice to meet you. See you again.
Thanks for all the questions, and thank you to the participants.
Yes. Thank you. Yeah, thank you very much for all participants. Yeah. Okay, thank you very much.
Bye.
Bye.